Okay, so this is the last week of classes. Next week we have no classes, okay? So let's try to finish our discussion on convergence. Well, let's continue and finish on Friday maybe. So last time we discussed the first mode of convergence, which is almost sure convergence. So we say some sequence xn, some sequence of random variables, converges to x almost surely if this sequence so the event that xn of omega converges to x of omega has probability 1. And we prove the characterization. So for every epsilon, we have the following. So the sum of the indicators so we count the number of such terms, xn minus x in absolute value, that are above epsilon, and this should be a finite number with probability 1 for every epsilon. So for every epsilon can go here or here, we show the two things are equivalent, right? But this is the one that is easier to check. So let's keep it here. So what we're going to discuss today is a second notion of convergence that is weaker than almost sure convergence. So this is called convergence in probability. So again, we have omega fp and some random variables that are real valued, okay, and another random variable x that are all real valued. So we say that the sequence xn converges to x in probability if for every epsilon we have that the probability that the distance between xn and x is larger than epsilon, goes to 0. Okay. So that's some way to define convergence of random variables, because you have a sequence of random variables and you have a possible limit x. And what you want to check is if the distance between xn and x is small. And by small, you mean that the probability that the distance between the two is large goes to 0 for every threshold epsilon. For every threshold epsilon, okay? Okay, we also write, so in this case, we write xn, so limit of xn is x in probability, or xn goes to x in probability. Okay, this is just a definition, right? So we should first understand why we have this notion as something that is weaker than almost sure convergence. So our first result is that if xn goes to x almost surely, then xn goes to x in probability. Right? So if you have almost sure convergence, then you have convergence in probability. So that's a larger set, right? So these sequences that converge to, that are convergent in probability is a larger set, right? It's a weaker condition, okay? Okay, so let's prove it. Okay, we're going to use the characterization of almost sure convergence here. So we have xn goes to x almost surely if and only if for every epsilon we have this, right? So the number of terms that are above epsilon is finite, almost surely. So what is the meaning of the finiteness? Well, you have this distance xn minus x above epsilon only for finitely many n. So this means after some n, let's say some capital N, index capital N, you're never going to have this thing, right? You're never going to have the indicator equals 1. You're always going to have indicator equals 0, right? This indicator is going to give you 0 after some point. So this means, let's say you have capital N, which is 5 million. So you have the indicator equals 0 for 5 million, indicator equals 0 for 5 million plus 1, plus 2, plus 3, etc., etc. What does that tell you? If you always get zeros for indicators, where does this converge to? 0, 0, 0 also converges to 0, right? So this implies that the limit of those indicators must be 0. Must be 0. With probability 1 again. Okay? And this is precisely the so-called nth term test, right? If you have a convergent series, the general term of this converges to 0. If you recall from calculus. But just by logic, you can also observe this, right? You don't need to remember that test. Okay, anyway, what does this tell us? So you have a sequence of random variables. Those random variables may be in blue. Okay, let's call it yn. Okay. So those random variables converge to 0, and they are also bounded by 1 because they are just indicators. So if you take expectations of those random variables, can you say that their expectation goes to the expectation of the limit, which is 0? So you have yn converges to 0. Can you say that expected value of yn converges to 0? Dominated convergence theorem. Okay, great. So by dominated convergence theorem, we can say that the expected, without the expected value, of course. So you have this with probability 1, right? The almost sure version of the dominated convergence theorem, right? So the limit of yn, so let me write what my yn is. It's just this, is 0, right? And what is this expected value? Expected value of the indicator of this. What is that? It's the probability that xn minus x is greater than epsilon, which is exactly what we have in the definition of convergence and probability. So we conclude xn converges to x in probability. Okay. Yes?
Can you give an example when the reverse doesn't hold?
Exactly, this is what we're going to do next. Okay, so the converse fails in the following example. Okay. So we want to have a sequence that converges to, that is convergent in probability, but not almost surely. So here's the example we're going to discuss. So let's say we have, let's pick the unit interval with the Borel sigma algebra. And the uniform probability, which is the Lebesgue measure. Okay? So we take this. Okay? So we have this unit interval. So the first random variable we're going to look at is just the indicator of the set, which is always 1. Which is always 1. Okay? Next time, we're going to chop it down into 2 equal pieces. So 1/2 and 1. So x2 is going to be the indicator of 0 to 1/2. And x3 is going to be the indicator of 1/2 to 1. Next time, we're going to chop it down into 3 pieces. 1/3, 2/3, 0 and 1. So x4 is going to be indicator of 0 to 1/3, 1/3 to 2/3, and so just to have intervals that are closed from the left and open from the right, I excluded point 1 just for elegance. Okay? And you continue like that. This is the construction. So if you have 1 omega fixed, okay? So in every picture, this picture, this picture, and this picture, you have only one of those random variables belonging to that picture. That gives you 1 for the indicator at point omega. At point omega. Okay? So we have x1 of omega is 1. x2 of omega is 1. x3 of omega is 0. x4 of omega is 0. x5 of omega is 1. x6 of omega is 0. In the next batch, you're going to have 4 random variables. 3 of them are going to give you 0. 1 of them is going to give you 1, and so on. So this means what? You're going to have xn of omega equals 1 for infinitely many n, and also xn of omega equals 0 for infinitely many n. And these are the only 2 possible values of it. So you don't have convergence. Xn of omega is not convergent. Right? For every omega. So we don't have convergence for any omega, so we don't have almost sure convergence. Because for fixed omega, we never have convergence. So we wanted to have something that converges in probability, but not almost surely. We don't have convergence almost surely. That's for sure. So the next question is, what is the limit in probability? So this is supposed to be an example of the existence of convergence in probability, but not almost sure convergence. So what is our limit in probability? Any guesses? What should be the limit in probability? Zero, right? So the intervals are getting smaller and smaller. So maybe the limit is 0 in probability. Okay. So this is our guess. And what we need to do is to check xn greater than epsilon, right? Because x is 0. Xn is positive because it's an indicator. So we just need to look at where this converges to. First, let's calculate it. For instance, can this, if epsilon is 5, what is this probability? Just 0, right? So this is 0 if epsilon is greater or equal 1. Right? Because we have strict inequality here. And otherwise, what is the probability? What is the probability? So what does that mean? Xn is greater than epsilon, let's say 0.5. Well, xn greater than 0.5 means xn is just 1, right? Because it is 0 or 1. So what is the probability that xn equals 1? Well, it is just the length of this. So this is 1. This is 1/2, and the other one is also 1/2. Then you're going to have 1/3, 4, 5, and 6. Etc. So slowly it's going down to 0, so you can convince yourselves that xn greater than epsilon is just 0. For epsilon between 0 and 1, and for epsilon greater than 1, it is always 0, so we always have this. So indeed, we have xn converges to 0 in probability. Okay. Yes. Well, just by inspection, right? Because in every picture we're partitioning the interval 0, 1 into several pieces. Since it's a partition, it can belong to only one. Okay? So you have, let's say, 0, 1 over n, 2 over n, 3 over n. So omega is in only one of those intervals. And of course, depending on the value of omega, you can determine that, right?
Example, in first case, said that it's in x5, right? x5.
Is 1.
No, it's 1.
Here. Yeah, just my omega. This is my red omega.
So we can arbitrarily find them also.
Of course. Just one realization in the picture. Just one realization. Of course, it's random, right? It's a randomly selected point from omega, space omega. Still, there is a partial converse to this theorem. So we've seen that the converse doesn't hold in general. What is true is that if you have convergence in probability, then you have an almost surely convergent subsequence. Not the full sequence, but that there is a subsequence. So let's state it as a lemma maybe. Xn converges to x in probability implies there exists a subsequence let me write it x and k, indexed by k now, with x and k goes to x almost surely. So here k goes to infinity. Okay. Okay, maybe I should remind you some corollary of Borel-Cantelli lemma from last time, because that's what we're going to use. Yes. So recall that some sequence, so suppose there is a sequence epsilon k of strictly positive numbers such that they converge to 0, k, and the sum of probabilities let me use y, okay? I'm not going to use it for the full sequence. Is finite. Then yk converges to y almost surely. Okay, so it's a corollary of Borel-Cantelli number 1 from Friday. Good. Why do we use this corollary of Borel-Cantelli? Because it has some relationship with convergence and probability, because these are the type of quantities that we would like to get the convergence of in convergence and probability, right? This is the type of probabilities that we look at. So let's see. Let's try to pick some epsilons that converge to 0, and the probabilities corresponding to those epsilons are going to sum to a finite number. So we're going to get some bounds for those probabilities whose infinite sum is a finite number. Okay? Let's begin with the epsilons. What we're going to do is just to pick 1 over n, because that's a very simple sequence that converges to 0. So for epsilons, we're going to use 1 over case. Okay? So we have that for every epsilon, the limit xn minus x greater than epsilon is 0. So what does that mean? Well, so if I take 1, okay, then there exists some n1 such that the probability that xn1 minus x greater than 1 is less equal 1 over 1. Okay? this looks maybe meaningless, so let me do it for 1 over 2. Then there exists some n2, okay? There exists some n2, and I can certainly pick it greater than n1, such that xn2 minus x greater than 1 over 2 is less than 1 over 2 to power 2. Why do I do that? Why do I do that? Because from this limit, I can use any epsilon I want. And I choose to use 1 over 2 to power 2 because 1 over 2 to case is a geometric sum which is finite. So at the end of the day, this is what we would like to have. And our y k's are going to be xn1, xn2, xn3, etc. So if we do it for 1 over k, then there exists some nk greater than nk minus 1, such that the probability that xnk minus x is greater than 1 over k is less than 1 over 2 to k. So these are our epsilon k's. And we have the sum of x and k minus x greater than epsilon k's, which is just 1 over k, is less equal what? Sum of 1 over 2 to k's, which is finite. Finite, geometric sum. So by this, by recall, x and k converges to x almost surely. So we extracted a subsequence that converges to x almost surely, although the full sequence, as in this example, may fail to converge almost surely. Okay? So there is a subsequence that is convergent almost surely. And there is even a further characterization of convergence and probability, full characterization in terms of almost surely convergent subsequences. So this is going to be a full version of this lemma. Okay? So xn converges to x in probability if and only if every subsequence, let's say x and k, has a further subsequence. So we're going to the third order, further subsequence, x and kl, okay, that converges to x almost surely. Okay. So we started by proposing convergence in probability as something that is weaker than almost sure convergence. Okay. But then we said, okay, although they are not equivalent, convergence in probability is weaker, we still have that if we have convergence in probability, then there is an almost surely convergent subsequence. What this theorem says is even stronger. Well, convergence in probability and convergence almost surely are not the same thing. But convergence in probability is equivalent to the existence of a further subsequence of every subsequence that converges to that same limit almost surely. Okay? So let's try to prove it. Okay? So let's go from the first statement to the second statement first. So suppose xn to x in probability. So for every epsilon, we have, just for convenience, I'm going to give it a name. Okay, this converges to 0 as n goes to infinity. So let xnk be a subsequence of xn. So, you know, if you have a sequence of real numbers that are converging to a 0, then every subsequence also converges to 0, right? This is convergence in real numbers, a fact from convergence in real numbers. And if you take this course, IE 500, you must have seen that, right? So if you have a sequence of real numbers that is converging to some limit, then every subsequence converges to that same limit. So the corresponding subsequence converges to 0. Okay, this is for every epsilon. What I'm trying to say is that the subsequence also converges to the same limit in probability. So the fact about convergence in real numbers just transfers to convergence in probability. Okay? So if you have a sequence that converges to some limit in probability, then its subsequence also converges to the same limit in probability. Okay? And by lemma, this subsequence has a further subsequence. There is a further subsequence, xnkl, that converges to x almost surely. Okay, so this was the easier part. So let's call it star, assume star. Now we're going to show that xn converges to x in probability. Okay, so now we show that xn converges to x in probability. So let epsilon be positive. We need to show that this converges to 0. This type of probability converges to 0. Okay. And this is equivalent to, so it is enough to, again, I'm using a fact from convergence in real numbers. It is enough to show that every convergent subsequence P and K epsilon converges to 0. Okay, so let's show it. Let P and K be a convergent subsequence. Okay, so corresponding to those numbers, there are, of course, random variables, right? So consider the corresponding subsequence of random variables. So why do we look at that subsequence of random variables? Because this is in our assumption, right? Every subsequence has a further subsequence that converges to x almost surely. So by the assumption star, there is a further subsequence x and kl that converges to x in, almost surely, but almost surely implies also in probability. Hence, also in probability. Hence, P and KL goes to 0 as L goes to infinity. Because this further subsequence converges to X in almost surely, hence in probability. So since we have it in probability, we can talk about the corresponding sequence of probabilities, so which converges to 0, Okay. So this is a convergent subsequence, and it has a further subsequence that converges to 0. So if you have a convergent subsequence, or let's say if you have a convergent sequence, okay, you know there is a limit, and one of the subsequences converges to 0. This means the true limit is 0, right? So since the limit of the subsequence is 0, since the original subsequence P and K is convergent, we must have that P and K goes to 0 as K goes to infinity. And this is exactly what we wanted to show. It is enough to show that every convergent subsequence converges to 0, and this subsequence converges to 0, so we're done. A bit puzzling and confusing, but it is not a deep result, deep idea. Okay? Just you need to play with, you need to go back and forth between the sequence of random variables and the sequence of probabilities, those probabilities, P and epsilons. Okay? And just to say something about convergence and probability, you use some very well-known facts for convergence of numbers, convergence of real numbers. Okay, any questions? Any questions about convergence and probability? So we have, this is the main fact, right? And this is an attempt to recover convergence and probability from almost sure convergence in a weird manner. So still, convergence and probability might look weird to you because, for instance, can we say things like, okay, xn converges to x in probability, yn converges to y in probability. Can we say, just like in calculus, that xn plus yn converges to x plus y in probability? Can we add those limits, etc.? So there is, luckily, some calculus for convergence and probability, some arithmetic. Okay? We're going to discuss this now. Here, calculus just means some rules of calculations. Okay. So just as a recall, so if you have a continuous function, it is also measurable. Okay. We never proved this fact in this course. But actually, this is true also in metric spaces, but also in Rn. Okay, you have a continuous function, then it is measurable. The reason is that so one way to define continuity is as follows. The pre-image, the inverse image of every open set is open, right? Some definition of continuity says pre-image of an open set is open if O is open. So I tried to avoid this during the course because I did not want to assume that you know open sets. But since many of you are enrolled in some other course in analysis, for instance, IE 500, now you might have known this fact, right? So another thing is that you can, if you have an open set, so if this is an open set, open subset of real line, you can also write it as a countable union of intervals, open intervals. This is for the real line. And once you have countable union of open intervals are Borel sets, countable union of them are Borel sets, so is Borel, which shows measurability. Okay. Well, why does this show measurability? Why is this enough to check only for open sets? Because, for instance, you can just look at open intervals, pre-images of open intervals, right? Okay. So this is some result that we sometimes used, for instance, in calculations, just to have Riemann integrability and so on, we assumed bounded and continuous functions. But we never questioned why they are measurable. Well, they are measurable, okay? They are measurable. And indeed, the Borel sigma algebra on the real line is also generated by collection of open sets, okay? Remember in chapter 1, we had a long list of collections that generate the Borel sigma algebra, right? Open intervals, closed intervals, other weird intervals. And also, it is generated by open sets. It is generated by closed sets, okay? So, and in general, if you have a metric space, just take the open sets of it. Just take the open sets of the metric space, just abstract metric space, okay? Then take the open sets. The sigma algebra generated by those open sets is called the Borel sigma algebra of the metric space. So there is some connection between continuity and metric spaces and topology and measure theory and probability theory, but we usually avoided such details, such connections, okay? But that is one point I just wanted to give a remark about. So continuous functions are measurable. That's all I wanted to say, okay? So the only point of discussing this result is as follows. So if you have xn goes to x in probability, and f is a continuous function, then f of xn converges to f of x in probability. For instance, if xn goes to x in probability, then sine of xn goes to sine of x in probability. Xn squared goes to x squared in probability. Things like that. Okay? So that's why it's useful. Just like in calculus, right? If you have some little xn's, real numbers converging to x in just in the usual real line sense, okay? And you apply a continuous function, take squares, cubes, etc., then you have this result, right? From calculus. So that's why I called it a calculus for convergence and probability. So let's try to show it. Okay, so we're going to use this characterization theorem. So, okay, proof. So we're going to show that this converges to f of x in probability. So let's use the characterization theorem. Okay, this is the characterization theorem because it is if and only if. Okay. So we want to show that f of xn converges to f of x in probability. So we need to take a subsequence. Let f of x and k be a subsequence of f of xn. So since so if we forget about f, if we just look at xn case, so this converges to so consider the corresponding subsequence x and k, okay? So by the theorem, it has a further subsequence, x and kl, that converges to x almost surely. Almost surely. Okay? Well, almost surely is just omega by omega, but except on a null set, right? So if you have x and kl goes to x, and f is continuous, so if you have it almost surely, and f is continuous, then for sure you can do it with f of x and kl, because it is just convergence of real numbers, omega by omega. By convergence in real line. Convergence. Okay. So this means what? So f of x and kl converges to f of x almost surely. This is exactly what we wanted to show, because we took a subsequence. Now it has a further subsequence that converges to the limit almost surely. So conclusion is that f of x and xn converges to f of x in probability. And I guess it's time for a break.